next presentation comes from CSCS with Ivano Bonesana.
Cool. Thank you. I would like to present today a little bit of what we are doing about automating the platform management of Alps with introduction of vCluster and vService concept. And we will start from the beginning, covering what is intended to be a typical supercomputer access, like intended to be like a user that submits jobs for scientific computation using data in a traditional way. Now, the point is that nowadays, taking a closer look to what supercomputer centers should provide, you'll see that there are a lot of services, a lot of variety of infrastructure and heterogeneous GPUs, resources like CPU node, storages, and services that has to be provided to users. So it's not just having jobs to run. And if we take a look, as we've seen these days, on the request, the word that you want to use a supercomputer does, you may see that we have set a bunch of variety in size from different communities, interactive sessions, different usage and use cases. So even the possibility to reutilize the results of computation for AI training, and so there is a bunch of complexity growing up around a system like supercomputer. And the point is that we have seen these days a lot of presentation about this. There is some kind of convergence between the cloud world and the HPC world. As we have seen, I won't be do a lot of example like here, but from the cloud world, where the high flexibility and the containers are very appreciated in even for scientific applications that are increasing, there is something that the HPC world that is much more related on high performance and a vertical integration, focused on results and time for solution, can bring, because the flexibility that it is demanded by users that the cloud environment provides is something that the HPC world has to become as a goal. So what we are proposing to join these two worlds is the concept of a versatile cluster that we would like to introduce. So concept to merge these two worlds are basically layering, introducing concept as platform, as vCluster, or we see infrastructure as a code. So making the deployment, making the cluster configurable and, let's say, quite abstract from the reality of the infrastructure we have. And then increase the performance and the flexibility using containers, as we have seen in the past days, or adding the HPC business logic as API, and web gateway to access the infrastructure like an option. All this, putting together, has given the idea of developing this concept that is the versatile software-defined cluster technology. In one word, the vClusters. Now, vCluster can be summarized in these points. So a set of components and practice that allow to partition the full amount of nodes that we have, and that is done by using the technology that Alps supercomputer provides us. making a vCluster defined as a collection of resources and services grouped together using a common use case. For example, machine learning, for example, weather and climate, and so. A group of vClusters sharing the same use case becomes a platform. And a platform is something that we offer to the communities that at CSCS want to do their job. And all of this is intended to be managed with a fully DevOps concept. So this means that we would like to make it flexible, also the deployment and the management of the partitioning of the supercomputer itself. And how do we perform this? Well, the Alps infrastructure is something is called an image-based infrastructure that allows to layer the operating system image that is deployed on each node following this schema. Also, we start with the hardware-based configuration within the operating system, and you can configure basically whatever layer up to the application level. Using this approach, you can configure each node freely because this image is not tied to each node, but can be used everywhere. So you can basically develop your image as you like, following all these layers are managed by Git repository, so you can compose it and deploy it on the entire cluster, let's say, creating this kind of configuration that is flexible. Moreover, what you can do is develop a set of layers dedicated to a use case and divide or partition the full set of nodes using these images, grouping them using the nodes as vClusters. So you can see here we have an example of what we have in Alps right now with Dane, Sentis, Tiger, and Clarion. This should be enough? No, that's the problem. The technicality offered by Alps is not flexible enough because if you can imagine, there is a lot of flexibility more required because the application layer, for example, has to be tied to the use case of the users that want to run jobs there. And even if you can imagine how many configuration changes has to be applied to the Slurm layer, for example, changing plugins, changing Slurm comps, changing options. Any option, any modification may be different for any use case. So you should be able to rebuild this image several times. And this takes a lot of time because it's not easy. And then moreover, the image cannot do all because file system, for example, is again focused on the usage of the different community. Or in any case, an extra layer is required to do the fine-grained configuration at the end of the deployment. So moreover, another limitation of this topic is that it's not so easy to develop the layers. So we cannot pretend that maintainers of this system have the knowledge of anything, any detail of any application they want to deploy, especially for the application layer. So what we want to do is to have more developer, more expertise involved in the process. How can we do this? Now, the idea is that to introduce what is called the vServices layer. So the image is tied, is reduced to the minimum required to work on the node. And then over that, vService deployment layer runs to deploy whatever it is needed to make the system run properly. In details, a service can be defined as a standard software-oriented approach to deploy applications and service on the nodes, running on the top of a minimal image. This means that basically the service are a system to deploy software on the nodes. it ensures to have higher flexibility because it is software. It has not, we don't have to rebuild the image to deploy and do changes. It speeds up the updates and upgrades, and it increases the number of contributors because developing this kind of disability should be simpler than modifying the layers of the images. And moreover, we have, since we are talking about software, we have a bunch of new dynamic features like rolling updates, staging, vClusters that we will see, and the possibility to reconfigure and move the nodes without rebooting, so in a live context. Basically speaking, the services are Terraform modules that originally was conceived to deploy nomad jobs on the resourcing that makes the configuration job on the nodes. Saying that, what we are developing in the last months, we are expanding the concept to deploy anything through Terraform models. So we can support from Kubernetes or whatever. Since we are talking again about software, because at the end of the day, these services are software, we exploit the workflow, the DevOps workflow in the deployment of the development and the deployment itself, the vCluster. Now, DevOps is a well-known software paradigm to deploy and develop and deploy application in a continuous way. How do we apply this to a platform and to a deployment on a vCluster? Is following these concepts. So a single source of truth as the Git repositories, where we have vServices and vCluster managed by Git, an automated process using pipelines to deploy everything on the nodes, and a management of changes based on feature branch and merge requests integrated with automated tests. So this principle becomes applied in this example, considering how a vCluster is configured. A vCluster is maintained in a repository, and the repository has two branches, the main and staging. Any changes applied to staging proposed to anyone can want to modify the system. Those changes are handled with merge requests that are tested locally on the staging by automatic system. And once per week, the merge requests are grouped together, discussed, and validated to be merged in the main deployment. The main branch deploys on the cluster physically. This process is iterative and can be replied and reproduced at any time. And anyone can create a new branch and a proposal for a modification that is then evaluated. So this makes the system very accessible by developers. And all of this is handled by pipeline automation. Now, taking a look to how the process should work, this is the system where we want to deploy and the feature we want to use. So we have the cluster itself on the right, and a Kubernetes cluster that handles services on the left, maybe triggered by and maintained by Argo CD. Now, what we want to do is to prepare a modification request using a set of vServices we want to deploy on the cluster, collecting them together, and when everything is fine for the deployment, triggering a Terraform pipeline that is able to deploy using the providers on the Nomad orchestrator provider that then is in charge to deploy the nodes themselves, deploying Kubernetes with all the services that are interested to be used. And all of this can be done in a simple way from the single source of truth that is the main in the cluster repository. All the secrets has to be kept outside of a accessibility of main repository using, for example, Vault, that is able to inject secrets wherever it is needed inside of the pipeline or inside of Kubernetes. Now, what do we expect to have when we deploy? Well, the pipeline runs, and Terraform is able to extract resources from what the service we are going to deploy. And those resources are then classified in this list you see on the left. And when the process runs, it basically step by step deploys the services on the nodes, differentiating what is going to be deployed on Terraform, on Kubernetes, what is going to be deployed on compute nodes, and what is going to be deployed on login nodes. So it's able automatically to deploy everything. We can also deploy, for example, security application on login nodes separately. We can deploy API like FileCrest with the part on Kubernetes that handles and manages the request from outside. But we can also deploy, for example, Jupyter Hub directly on Kubernetes without involving nodes. And all of this is done in a single repository and in always the same way. So how does this process work? Well, as I said, it's based on Terraform. So the vClusters definition is a composition of Terraform modules that are the vServices, as we said. The vCluster defines also the providers, Terraform providers that are allowed to deploy the application directly on the target. So it could be nodes with Nomad or whatever it is needed. And we follow the standard plan apply from Terraform. In the pipeline, you see we have 3 stages. After validating the input of the code, we plan the changes. So Terraform is able to compare what is deployed in the target system and what is going to be changed, compiling a list. And then using this comparison, it's able to apply only the modification we have requested without touching anything else. So the Terraform state ensures that only the changes that we are effectively approved in the merge request are going to be deployed on the system, altering it. And this is why we are using Terraform in deployment. Now, having a closer look to the cluster, I said it's just a list of modules, as you can see here. And basically, each vService is used as a repository with a version tagged like this. So you can choose wherever you want to pull the service and which version you want to deploy. Moreover, you have to provide providers and a set of variables that can be used to configure the entire deployment. I said here like global variables, but they are intended to be CI/CD and injection from secrets or other configuration variables. Taking a look to what the vServices is. Actually, we can describe it as a repository with a standard structure that we provide to the developers as a template. And the template allows to facilitate the approach, having basically it is something that is ready to be deployed. So we have 2 versions of the template. We can work with Ansible or Bash script. We'll show you later how. And basically what we ask to the developer is to use this structure of main variables and output to basically develop the code. How? We provide this set of files already set up so that they can basically focus on the job that has to be done. So the job is, you can see here in the example main.tf, is a normal job that is basically something like this. Everything you see here is provided in a template, so the user has just to modify the highlighted part of the code, and he can basically write his own script using bash or rely on Ansible. If they rely on Ansible, where we have most of the services now are becoming Ansible based, we just run here the playbook, and the user can provide his own playbook as he prefers. You may see here that the structure of this template has some start deploy, end deploy script, and so start run and start remove that we provide as a system to synchronize and let's say organize the deployment on the node. When you deploy a system, and now I'm focusing on the compute nodes, on the login nodes, not about the Kubernetes part. What we are doing is basically launching a sequence of jobs that have this sequence of states. So in each state, the user can define, the developer can define what has to be done. And the sequence of the deployment is managed by our system that we provide already on the node. We ask to deploy a vService transiently. It means that it should remove what is installed at each cycle. This is because it makes easy to switch from one deployment to the other, as I will show you in a while. When we start to deploy a system like we did before, what we expect is that we provide to the Nomad server a set of status that has to be applied on each node. The status represents the set of jobs that has to run. And the orchestration works like this. Nomad has a secure agent server architecture that deploys, is already deployed on all of the nodes in the minimal images, as we said before. And these agents connect to the server, ensuring that they have a secure privileged access directly on the nodes itself. So when we provide a deployment, we provide a set of the service of the basically of jobs that are then installed, and each job is an isolated application that runs in a sandbox that Noma provides, but with access as a root to the system. So it can install, it can move, it can do whatever it is needed, again, as Bash or Ansible. And we can also specify constraint on the node, so we can specify where these jobs are deployed. The dynamic of the deployment using the agents ensure that if a node is joined to a server and Nomad is configured by Terraform to deploy the jobs on that node, it automatically provides them. So you don't have to do basically anything else that tagging the node or rebooting it. Moreover, there is a concept that is the sub-vCluster, as we have defined, that allows us to define a group of nodes using the concept of data center that is in Nomad. That basically groups the deployments and allow to define which kind of sequence, which kind of jobs and vService are deployed on which node. And this is done entirely on software layer. It means that if I want to, for example, move a node from one deployment, from one sub-vCluster, sorry, to another one, anything I should do is changing the data center, and Nomad will provide the deployment as you see here, automatically. And this is what we are trying to do to create, for example, staging partition, but also testing environment directly from the running job, the running nodes, without the rebooting. This flexibility should be interesting to allow into testing better and develop better. What we provide to the developer again is also, I already said, the template, but we have also a development pipeline integrating that templates that allows them to test and verify what they are doing on a secure environment that is a couple of, let's call them test cluster, like you can see here, like Dina TDS and Matter TDS, with virtual machines or real nodes. Then we provide an integration, all which kind of stable vCluster that it can be used to test on the field, services that are deployed, like Wilder and Xenon in this case. It can be also used to develop container engine or whatever application because they are basically stable. But also this system is also portable, and nothing prevent to be used some kind of cloud or virtual machines to emulate what the nodes are. So all of this can be done basically on their own laptop, independently of what we need from what we can provide in the entire system. That depends a little bit on what kind of service we are deploying and which kind of hardware architecture is used. In conclusion, we have a lot of work done, but we have also a lot of work to do. And what I've shown you here is something that we already have, but it's also we're going to do. And yeah, I mean, today the number says that we have 16 vClusters deployed, 8 are incoming with this technology. And about 20 active services means that we have much more developers involved in this, and a lot of work in the last 2 years. The requests that are coming is to have better testing and templates, and easy access to TDS with automation more integrated with the infrastructure. We are lacking a little bit the conjunction from the images to the services. And then what are going to be deployed in the next month that are already done is some improvement in the deployment sequence to make it working better, as I've shown you in the slides, to be honest. And implementing rolling updates, maybe orchestrated by Slurm, that allows us to deploy updates on the nodes while jobs are still running, queuing them in the normal workflow. And then, moreover, working more on the vCluster, on the sub-vClusters to create staging and environment that can be used easier. More feature can be about this topic because we still need a better testing for vCluster deployment. We still to improve the staging area and the observability feature that we need to provide to monitor the deployment. Thank you.